In the late 1930s, Europe's automotive future was supposed to belong to established giants like Fiat, well-funded, well-connected, and backed by industrial empires. Poland was not meant to compete. It lacked oil, capital, and political stability. Yet, in a modest workshop in Warsaw, an engineer named Rudolf Pawlowski quietly challenged that assumption. Instead of copying proven solutions, he rewrote the rules of engine design itself. What emerged was a cooling concept so unconventional that it sounded reckless, and yet it worked. Not better marketing, not bigger budgets, just physics, necessity, and an idea no one else dared to try. Poland's desperate energy gamble. Picture this. It is 1938 in Warsaw. The cafes are bustling, and the trams are rattling down the tracks. But if you look closely at the faces of the people walking down Marszałkowska Street, you can see a specific kind of tension. Poland is a nation living on borrowed time. To the west, you have the industrial war machine of Nazi Germany, revving its engines. To the east, the Soviet Union is watching with hungry eyes. You are a country squeezed between two superpowers that do not just want to defeat you, they want to erase you from the map. In the halls of the Polish Ministry of Industry, the generals and politicians are staring at a map that tells a terrifying story. It is a story of geology and survival. Poland in the 1930s is an industrial anomaly. If you dig a hole in the ground in the Silesia region, you hit some of the richest, densest black coal in the entire world. It is everywhere. In fact, 96% of the nation's industrial power comes from burning this black rock. Coal is safe, coal is domestic, coal is yours. But here is the catch. You cannot put a lump of coal into a tank. You cannot shovel coal dust into the fuel tank of a truck that needs to move supplies to the front lines. The modern world is rapidly moving away from steam and toward the internal combustion engine. That means diesel and gasoline, and Poland has almost none of it. Every drop of fuel that powers the growing fleet of trucks and buses has to be bought on the international market, often from the very neighbors planning your destruction. The strategic nightmare is simple. The moment the first shot is fired, the borders close. The oil stops flowing. The tanks stop moving. The army starves in weeks. This is where a man named Eugeniusz Kwiatkowski steps in. He is the Minister of Industry and a man who understands that true independence requires more than just a flag and an anthem. It requires factories. He establishes the National Engineering Works, known as PZINs. This is not just a car company. It is a strategic asset. The mandate given to the engineers at PZINs is brutal in its simplicity. They are told to build a domestic automotive industry from scratch. They license designs from Fiat in Italy, but they cannot just copy them. The roads in Poland are rough, unpaved, and unforgiving. The winters drop to temperatures that crack engine blocks. The order is to harden everything, make it tougher, make it last longer. In the middle of this high-stakes engineering fever dream stands Rudolf Pawlowski. He is not a wild-eyed theorist or a celebrity scientist. He is a pragmatic engineer looking at the world with clear eyes. He looks at the massive stockpiles of Silesian coal sitting in the rail yards. Then he looks at the expensive barrels of imported diesel oil. He realizes that the survival of his country depends on solving a chemistry problem. He asks himself a question that sounds impossible to everyone else. Why are we spending a fortune buying oil from our enemies when we are standing on top of a mountain of fuel? Pawlowski decides that he is not going to try to find more oil. He is going to force a diesel engine to eat coal. The engine that ate coal. You might think that pouring pulverized rock dust into a precision machine is a recipe for a hand grenade. In the world of internal combustion, solids are the enemy. If you get even a tiny amount of dirt in a cylinder, it scores the walls and destroys compression. So the idea of intentionally injecting coal, which is essentially combustible rock, sounds like mechanical suicide. Most engineers in the 1930s thought so too. They had tried blowing dry coal dust into engines with compressed air, and the results were always the same: violent, unpredictable explosions and engines that seized up within minutes. Rudolf Pawlowski looked at those failures and realized everyone was solving the wrong problem. He stopped trying to make coal behave like air and started making it behave like a liquid. His breakthrough was the coal oil slurry. Instead of a cloud of dry dust, he created a thick black soup. He ground Silesian coal down to a micron-level dust, so fine it flowed like water, and suspended it in a small amount of heavy oil. This wasn't just a fuel, it was a liquid engineering system. The magic happened inside the cylinder. In a standard diesel engine, you compress air until it gets hot enough to ignite the fuel. In Pawlowski's system, the heavy oil acted as a pilot light. It ignited first, providing a reliable, controlled flame front. This flame then ignited the coal particles. Instead of a single cylinder cracking bang, you got a two-stage burn. It was a smooth, sustained push on the piston, providing massive torque without the destructive shock waves of dry dust. But the real genius, the part that genuinely outsmarted the physics of the time, was the cooling trick. Engines running on experimental fuels usually failed because they got too hot. The metal pistons would expand and weld themselves to the cylinder walls. You would expect coal, which burns hot and slow, to make this problem worse. But Pawlowski discovered a thermodynamic loophole. When you inject that cold coal slurry into the hot cylinder, the coal particles act like millions of tiny heat sponges. Before they burn, they have to heat up. Because coal has a high specific heat capacity, it absorbs a massive amount of thermal energy from the air around it, just to reach ignition temperature. This effectively sucks the dangerous heat spike out of the combustion cycle. It cools the engine from the inside out at the exact moment it is most vulnerable. It is a primitive form of regenerative cooling, the same principle used in modern rocket engines, applied to a city bus in 1930s Poland. Of course, the chemistry was only half the battle. The ash left behind was still abrasive silica. To handle this, Pawlowski redesigned the mechanical heart of the engine. He bored out the fuel injectors and hardened them with industrial alloys to stop the slurry from clogging the nozzles. He then re-engineered the piston rings. Standard rings just seal pressure. Pawlowski's rings were active wipers, designed to scrape the cylinder walls clean with every downstroke, pressurizing the lubrication system to force the ash out before it could mix with the oil and turn into sandpaper. This was not a desperate fix for a poor country. It was a sophisticated, self-regulating thermodynamic loop that turned a rock into a fluid and a liability into an asset. David versus the wood stove. To really understand the magnitude of what Pawlowski achieved, you have to look at the competition. Just across the border, the German automotive industry was the undisputed heavyweight champion of the world. Companies like Daimler-Benz had massive state subsidies, thousands of engineers, and the most advanced laboratories on Earth. They were also trying to solve the fuel problem. The Nazi state was obsessed with autarky, total self-sufficiency, and they needed their trucks to run without imported oil. So, what did the limitless budget of the German Reich come up with? They invented the Holzgas, or wood gas generator. And honestly, compared to Pawlowski's work, it was a joke. The German solution was effectively to strap a giant wood-burning stove to the bumper of a truck. You would fill a massive metal silo with firewood or charcoal, light a fire, and wait, and wait. It took about 20 minutes just to generate enough gas to start the engine. Once you finally got moving, the performance was miserable. Wood gas has a terrible energy density, so these vehicles lost anywhere from 30 to 50% of their horsepower. They were heavy, they were slow, and they looked like a steampunk nightmare rolling down the Autobahn. Pawlowski's approach was the complete opposite. He didn't add a chemical plant to the outside of the bus, he changed the chemistry inside the engine. Let's look at the tail of the tape. If you were a German bus driver in 1938, you were waking up half an hour early to stoke a fire. If you were driving a Pawlowski bus in Warsaw, you turned the key and the engine fired instantly. That is the beauty of compression ignition. While the German trucks were struggling to climb hills with half their horsepower missing, the Polish coal slurry buses were running at nearly full power. The power loss in Pawlowski's system was less than 10%. This is the classic David versus Goliath story. At the same time Pawlowski was tinkering in a workshop in Warsaw, Mercedes-Benz was spending the modern equivalent of millions of dollars developing the legendary Silver Arrow race cars like the W154. They were chasing speed and complexity, pushing the limits of liquid fuel. Meanwhile, Pawlowski was chasing utility. He was stripping the problem down to its bones. The result was embarrassing for the giants. The German engineers eventually realized that this Polish unknown had solved the problem they had given up on years ago. The economics were undeniable. Running a bus on wood gas saved money, sure, but it cost you time and payload capacity. Running a bus on Pawlowski's coal dust reduced fuel costs by 90%, with almost zero penalty in performance. That number, 90%, is the kind of efficiency gain that topples empires. It meant Warsaw could afford to triple its bus fleet for free. It was elegant, it was cheap, and it worked. And that is exactly why Mercedes-Benz came knocking on his door just before the tanks started rolling. 50,000 miles of proof. Theory is a wonderful thing, but the streets are where engines go to die. You can run a prototype on a test bench in a sterile laboratory for hours, but that does not tell you what will happen when you are stuck in traffic on a freezing Tuesday morning. Rudolf Pawlowski knew that if his coal slurry engine was going to save Poland, it had to survive the daily grind of the capital city. So, in 1938, he moved his experiment out of the workshop and into the heavy stop-and-go chaos of Warsaw. The vehicle chosen for this trial was the Polski Fiat 621R. This was not a delicate lightweight car. It was the workhorse of the Polish municipal fleet, a heavy-duty bus chassis designed to carry 25 passengers and withstand the punishment of cobblestone roads. Pawlowski modified these beasts with his specialized injection system, filled the tanks with his black coal soup, and sent them out to pick up real passengers. The skeptics were already writing the obituary for these engines. Common engineering sense said that even with the cooling trick, the coal ash would inevitably destroy the cylinders. They predicted that the microscopic silica particles would act like sandpaper, grinding the piston rings down to nothing within a few hundred miles. But as the weeks turned into months, the buses kept running. They ran through the slush of winter and the heat of summer. They idled in traffic jams and hauled full loads up the hills of the Vistula escarpment. By the time the trials concluded, the test fleet had logged over 50,000 miles. That is a staggering distance for an experimental technology in the 1930s. When the engineers finally tore the engines down to inspect the damage, they were stunned. The wear on the cylinder walls and piston rings was negligible. Pawlowski's pressurized lubrication system and active wiper rings had done their job perfectly, flushing the ash out before it could do any damage. But the drivers noticed something else. The driving experience was different. Unlike the German wood gas trucks, which felt anemic and breathless, the coal slurry buses pulled hard. The combustion of the coal particles was slightly slower than liquid diesel, which created what engineers call a fat expansion stroke. Instead of a sharp, violent spike of power, the coal provided a long, sustained push on the piston head. This massive low-end torque was perfect for a heavy bus starting from a dead stop. Then, there was the economic bombshell. When the city accountants looked at the books, they realized the implications of Pawlowski's work. Running a bus on coal dust, which was essentially a waste product from the mines, cost 90% less than running it on imported diesel. For the city planners, this was not just a saving, it was a revolution. It meant they could theoretically triple the size of the public transport network without spending a single extra zloty on fuel. It was the dream of every municipal government, a better service that cost almost nothing to run. The Warsaw trials proved that the coal engine was not just a curiosity. The enemy wants the keys. By the winter of 1938, the results coming out of the Warsaw bus trials were too loud to ignore. Information flows like water, even across borders that are bristling with soldiers. The reports landed on the desks of the top brass at Daimler-Benz in Stuttgart, and the reaction was stunned silence. You have to remember that the German engineers considered themselves the masters of the internal combustion universe. They had the state funding, the materials, and the legacy. Yet here was a report stating that a municipal engineer in Poland had successfully run a fleet of heavy buses on coal dust for 50,000 miles without destroying the engines. The German response was not to dismiss it, but to try and buy it. In the early months of 1939, just as the political situation was reaching a boiling point, Mercedes-Benz opened a channel of communication. They wanted to license the technology. Specifically, they wanted the designs for Pawlowski's hardened injectors and the chemical formula for his slurry. This interest exposes a massive crack in the German industrial armor of the time. The Nazi state was pouring billions of Reichsmarks into the Bergius process. This was a method of turning coal into synthetic liquid fuel through high-pressure hydrogenation. It worked, but it was a thermodynamic nightmare. It required massive chemical plants, huge amounts of steel, and consumed a vast amount of energy just to create the fuel. It was brute force engineering. Pawlowski had found a shortcut. He looked at the coal and realized you did not need to build a refinery to turn it into liquid. You just needed to pulverize it and trick the engine into accepting it. It was elegant. It bypassed the entire synthetic fuel industry and delivered energy independence right at the fuel tank cap. For Mercedes-Benz, this was the holy grail. It offered a way to power a military and industrial fleet without building a dozen more synthetic oil plants. The irony here is almost suffocating. At the very moment the German military was finalizing the operational plans for Case White, the invasion of Poland, their industrial leaders were trying to acquire the technology that could have made the Polish economy self-sufficient. It is a stark contrast in philosophies. The German approach was defined by autarky, which often meant incredible complexity and massive scale. The Polish approach, driven by necessity, was about resourcefulness. It was about taking a standard Fiat engine, looking at the piles of coal in Silesia, and making them work together with nothing but clever physics and precise machining. The day the future died. September 1st, 1939. That is the date when the clock stopped for Polish engineering. When the German Wehrmacht crossed the border, they did not just bring tanks and artillery, they brought an end to an entire era of independent thought. The invasion did not merely redraw the borders on a map, it erased decades of scientific progress in a heartbeat. The National Engineering Works, PZINS, was immediately in the crosshairs. In modern warfare, you destroy the enemy's ability to build, and PZINS was the heart of Polish construction. The factories where Pawlowski had spent years perfecting his coal slurry engine were bombed, shelled, and eventually seized. But the initial invasion was only the first blow. The true death knell for the technology came later, during the Warsaw Uprising of 1944. In the brutal street-to-street fighting and the subsequent systematic demolition of Warsaw by German forces, the laboratories were turned to ash. The prototypes of the coal buses, the experimental injection rigs, and most critically, the handwritten formulas for the chemical stabilizers in the slurry, all of it was buried under millions of tons of rubble. But machines can be rebuilt. The deeper tragedy was the human cost. The occupation of Poland was characterized by the deliberate targeting of the intelligentsia. The professors, the scientists, and the engineers were hunted down. Men of Pawlowski's caliber were seen as threats because they carried the knowledge of how to build a nation. Many were executed in massacres that wiped out the country's best minds. Others were rounded up and forced into slave labor, their brilliance redirected at gunpoint to build weapons for the very empire that was destroying their home. When the smoke finally cleared in 1945, the geopolitical landscape had shifted beneath Poland's feet. The country found itself in the shadow of the Soviet Union. The new communist government in Warsaw had different priorities. The logic of the coal engine, independence and self-sufficiency, was dangerous to the new order. The Soviet strategy was to bind their satellite states through energy dependency. Poland was ordered to export its high-quality coal for hard currency and import cheap oil from the Soviet Union. The strategic imperative that had driven Pawlowski to invent his engine simply vanished. The technology did not fail. The physics of the bizarre cooling trick worked just as well in 1950 as they did in 1938. But the world that needed it was gone. The coal slurry engine was not defeated by a better design. It was buried by politics. It became a dead technology, a relic of a brief moment when a group of engineers in Warsaw proved they could outsmart the world, before history came crashing down on top of them. How Pawlowski invented the future. We study Rudolf Pawlowski today not because we want to bring back coal-powered buses. In an age of climate anxiety, burning coal dust is obviously not the future. But the way he solved problems is a masterclass for any modern engineer. We have a word for it now. In India, they call it jugaad. In the West, we call it frugal innovation. It is the art of achieving high-performance results with severely limited resources by completely rethinking the constraints of the problem. Most engineers wait for the perfect conditions. They wait for the perfect fuel or the perfect material. Pawlowski did not have that luxury. He looked at a flawed, difficult material, dirty coal dust, and asked what his engine needed to do to handle it. He did not try to force the world to change. He changed the machine to fit the world. That is a mindset that is becoming increasingly valuable as we face our own resource crunches today. But there are two specific technical legacies that stand out. The first is a frustrating mystery. We still do not know exactly how he kept the coal dust suspended in the oil. If you mix coal dust and oil in a jar, the coal eventually settles to the bottom and turns into a thick sludge that would clog any fuel line. Pawlowski solved this. He developed a specific chemical recipe using surfactants that kept the mixture stable as a colloidal fluid. When scientists in the 1970s and 80s tried to revisit coal slurry fuels during the oil crisis, they struggled with this exact stability problem. Pawlowski's specific formula is one of the great lost recipes of industrial chemistry, right up there with Roman concrete. The second legacy is the cooling trick. Using the fuel itself to manage the heat of the engine is a concept that was decades ahead of its time. Today you see this exact principle in the most advanced machines on Earth. In hypersonic scramjets and liquid-fueled rockets, engineers circulate cryogenic fuel through the walls of the nozzle to keep it from melting before injecting it into the combustion chamber. It is called regenerative cooling. Rudolf Pawlowski was applying this same advanced thermodynamic concept to a municipal bus in Warsaw in 1936. Outsmarting the impossible future. Rudolf Pawlowski stands as the ultimate proof that engineering is not about the size of your budget, but the clarity of your vision. While the industrial giants of Europe were burning millions to chase complex synthetic fuels, he achieved a 90% efficiency gain with a grinder and a mixer. He took the impossible problem of burning abrasive rock inside a delicate engine and turned it into a competitive advantage. His bizarre cooling trick was not a lucky accident. It was a sophisticated piece of physics that outmaneuvered the research and development departments of the most powerful automotive companies in the world. The tragedy of this story is not just the loss of a machine, it is the loss of a different future. We can only guess what the 20th century would have looked like if the Pawlowski engine had been allowed to mature. Perhaps we would have been less dependent on the volatility of global oil markets. Perhaps we would have learned sooner that an engine can run on almost anything if you are clever enough to ask the right thermodynamic questions. But even though the blueprints were burned and the buses are gone, the philosophy remains. Pawlowski teaches us that the best solution is often the one right under our feet. He did not wait for a perfect world. He engineered a solution for the one he lived in. In the end, he did not just save a car or a municipal budget. He demonstrated that true innovation is about questioning the assumptions that everyone else accepts as fact. That is a legacy that no amount of rubble can bury.